Hey, hello everyone. We are from Group 1. We're going to explain about the code check of the data world, specifically on understanding about the key value store. And our group contains of me, Jawan Antiri Momoko, and Muhammad Zulfan Abdullah Ghani, Muhammad Zuza Romero, and the last one is Faisal Musharraf. Okay, we just jump to the agenda. We have four agendas here: the concept and the analogy of the key value, the architecture, consistency and availability, and also the real-world use cases and summary. Okay, the first one is the concept and analogy. We must understand about what is a key value store and why is it different from a standard database. So a key value store is the simplest form of the database. It abandons rows and columns for a simple map. Okay, and then to understand thoroughly, let's use the code check analogy. When you arrive at the theater, you hand the attendant your code. Okay, that's the value, and then the piece of data. In return, they give you a number ticket. That's the unique key. Okay, understand this? Now we move to when you want to get your code back. You must use the ticket number, right? The key. And then you cannot walk up and say, give me the blue code with the silver buttons. You cannot do that. You only ask by the ticket number, the key. The result is in incredible speed. The attendant doesn't have to search the whole room for the code with blue buttons. They go straight to the hook number that suits the key you give to the employee. And then we move to why we abandon the SQL. The problem with SQL is the relational database, like MySQL, are like an Excel sheet. And if you have 1 billion rows, such as many rows, finding one item can be slow and it cannot be perfectly optimized, okay? That's why we use the key value. One of the advantage is it is schemaless, so the database doesn't care if the value is a text, an image, or a video. It is just stores a block of data against a unique ID. Now we move to the architecture under the hood, and it will be presented by Faisal Musharraf.
Okay, now I want to explain about the architecture under the hood. Next. So in here, we have the right problem. So it showed us the what I'm going to show you. How does a key value store manage to store data so quickly? The challenge lies in writing data to disk. If you have 1,000 entries and you have to find the perfect alphabetical or numerical spot for every new entry, you spend a lot of time just reorganizing. So this slows you down your application. Next. So that's why we have the messy desk analogy, or LSM3. So the solution is an elegant architecture used by systems like Facebook's or RocksDB's and Google's LevelDB's called LSM trees or log structured merge trees. So let's use the messy desk analogy. Imagine a very busy librarian. First, we have a mem table, or we can call it the desk. When new books or data arrive, the librarian doesn't stop to shelf them immediately. They just pile them on their desk in a rough, quick order. This is done entirely in computer memory and is incredibly fast. The second one is SS table, or we can call it the box. When the desk is full, they shove all the books into a sealed box and put it aside. This is called flushing to disk. The third one, we have compactions, or we can call it the cleanup. So later, when the library is quiet, they open all the boxes, property, sort the books, and put them on the main shelf. So the system is prioritized write speed, getting the data into the system as fast as possible over immediate, perfect organization. This is absolutely critical for modern applications like Facebook or Instagram, where billions of pieces of data are being written every second. And then next, we want to explain the consistency and availability by Zosa.
Okay, and result, consistency and availability, the Amazon model. How do we keep data safer when computer crash? Based on Amazon Dynamo paper. On this slide, we look at the breakthrough introduced by Amazon Dynamo system. The source of these concepts comes from the paper Dynamo, Amazon's highly available key value store, published in SOSP 2007. This paper became foundational for many modern distributed databases. The central problem Dynamo addressed was simple but critical. If the server responsible for storing a particular key crashes, the key and therefore the data associated with it would be inaccessible or lost. In large-scale distributed environments, this risk becomes unacceptable, especially for systems that must operate continuously. Dynamo's solution was use replication combined with eventual consistency rather than relying on a single server to hold the key. Dynamo distributes and replicates the key across multiple nodes. This ensures the system remains resilient even when individual machines fail. The diagram on the right illustrates where Dynamo-inspired systems fit in the broader CAP landscapes. It shows the trade-offs among consistency, availability, and partition tolerance. Many modern databases such as Cassandra, CoastDB, Redis, and MongoDB adopt the design principle influenced by Dynamo and navigate similar trade-offs. Hmm. Uh, on the next slide, I will explain how distributed data systems share information by using a simple analogy. First, in a section label analogy, we can imagine a group friend sharing a secret with repression the data. You tell one friend the it correspond to node A. Node A then immediately pair that secret to two additional friends, which is we can think as of node B and node C. If node A becomes unavailable or crashes, node B and node C still retain the secret. This illustrates how data can remain accessible even when an individual node fails. The second section focuses on eventually consistency. Here, the key idea is the different nodes may not receive the information at the exact same time. For example, node C might learn the secret a few seconds later than node B. During the short delay, their views of the data differ. However, given the node time, all nodes recovers and ultimately agree on the same information. This captures the essence of eventual consistency in distributed systems. Finally, in the real life section, the slide provides a practical example. Sometimes when you delete an email, it briefly continues to appear on your phone before disappearing. It happens because the servers responsible synchronizing your devices are still in the process of exchanging updates, essentially gossiping with another until they reach a consistent state. Overall, this analogy helps illustrate how distributed systems communicate and how temporary inconsistencies arise while nodes work towards agreement. Next.
Then we have the last part is a real world
Alright.
use cases and summary. Next. So we have Redis and memory speed. So our final part covers where these systems really shine. So the most popular modern key value store is Redis, which is to take a concept of the speed in the extreme. So unlike Dynamo and RocksDB, which is write to a hard drive, Redis store the entire code check entirely in RAM. So this makes then it nanoseconds fast. So it is a tool of choice for catching hot data, the information, you'll need it right now. So and then when to use it. So when you use the key value store, whenever you need binding speed or for a simple lookup, first one is shopping cart. The key is your user ID. The value is the list of the items in your cart, and it has a load instantly. And then we have session management. So when you log into a website that logins, there is a key value pair that needs to be checked every time you click. And then leaderboard. In gaming, the key is the player ID. The value is their score. A key value store keeps the list constantly updated and quickly accessible. Next, we have conclusion. So conclude to wrap all of these things are so is the key value store is all about high speed to simplicity. So it's like a simple map. For example, tickets equal to code. And then it writes fast using a messages method or the LSM trees. It survives crashes by gossiping, replication, and it powers the speed of the modern internet by catching. I think that's all for our group. Sorry if there is any mistakes we've made. And thank you very much.